All right, next, let's see if we can identify what part of the world we're looking at in terms of like North Pole or equator or some other intermediate latitude. Here, we have stars moving parallel to the horizon. Okay. So where do you suppose we are? And some of you might be very observant and see that that's a polar bear sitting there. And so that would be a hint. But that's not the kind of hint I would give you on an exam. And so it turns out that when the stars are moving parallel to the horizon, you're near the North Pole. And so we might wonder then, well, how can you be so sure? And so the answer then is, well, look straight overhead. Now it's hard for me to do this on a flat thing because it would actually be looking up like that. Now let's imagine the North Star is way up there, but that's straight over your head. Then remember that all of the stars are going to go in counterclockwise circles around the North Star. Okay? And so if you're near the North Pole, then the North Star is overhead. And so if you trace that down then to a counterclockwise circle near the horizon, that's going to be moving parallel to the horizon. So this is the direction or the path of stars. It's a tangent to the circle. So that's what you expect to see then when you're up near the poles, is the path of the stars near the horizon, moving parallel to the horizon. Now what about here though? Where we see them going vertically. Well, again, you can use the hint of the palm tree, and that might clue you into the fact that we're near the equator. And so that would be correct. So here then, we're looking near the equator, then the North Star is right on the horizon. Imagine that this is the North Star here. And of course, you'd need to have a good horizon view. If you had trees in your way or mountains or whatever, then you wouldn't be able to see it because it would be below the horizon. But with a good horizon view, here's the North Star. We'll follow that same pattern of the stars describing counterclockwise circles about the North Star. And so we can see then that if you're on the right side of this North Star position, the stars would be moving up. If you're on the left side, and so this would basically be then the western side. This would be the eastern side. Stars would be moving up over here. The stars would be moving down over there. But in either case, the motion of the stars is vertical near the equator. So it's both of these motions, the motion near the poles and the motion near the equator, is still consistent with the idea that all of the stars appear to be describing counterclockwise circles about the North Star. Okay? But what if we were in this kind of a position so that we saw the stars coming in diagonally? Where do you suppose we'd be then? Well, if we think logically in terms of what we've already discussed, it might seem reasonable to say that the position would be somewhere between the equator and the North Pole. For example, San Luis Obispo, where we live. Then the stars would move along diagonal lines. Okay, so maybe something more like this. Okay, so if the North Star isn't 90 degrees above the horizon, then what you can see then is that when you're near the horizon, either on this side or on that side, you're taking a cross-sectional view of something that would be a circle, but you're not in the middle of the circle. So that means that these wouldn't be horizontal lines, but they wouldn't be vertical lines either. And so in other words, the North Star isn't at the horizon, but it's not straight overhead. So you're kind of taking something like this and cutting it off here. And so if you do that, then the tangents to these curves along these lines are going to be diagonal lines. And so that's what we expect to see around here then, is that near the horizon, the stars move along diagonal lines. Okay, so that takes care of being able to find our longitude and what we expect to see at different longitudes above the equator. But what about latitude? How do we know what the time zone is, for example? Okay, and so with longitude, we can we need some kind of a standard timekeeping device. Latitude, we can be cruising along in our ship. We can look up at the North Star, see what north latitude we're at by the angle of the North Star above the horizon. Okay, so if we are noticing that the North Star is 40 degrees above the horizon, you go, okay, well, we're going north. Now it's time to go due east back into our port in Lisbon, okay, which is at 40 degrees north latitude. So, but what if we're like Columbus and we're going this way and we want to know how far we've gone in the longitude direction? Okay, so we can think of latitude this way, these kind of stripes, along the axis that connects, that's why I remember it, I don't know if that's a good way to remember it, but it's along this axis that connects the North Pole to the South Pole. They call it longitude. Okay, so this way, we also need to be able to identify which part of the Earth we're at in this direction as well. And so for longitude then, we need a timekeeping device. And if we're trying to navigate on a ship, it needs to be able to work on a ship. So we've got part of the problem solved. With latitude, you just look at angle of the North Star above the horizon. And also, if the North Star, you might say, well, what if it's bad weather and you can't see the North Star? Well, then, in the time of Columbus, they also had star charts, too, or sun charts, I should say, in which, as a function of the latitude, you could measure the maximum height of the sun above the horizon. And that would also give you your latitude. And so those sun tables were also very useful and used in conjunction with the North Star. Because it's going to be easier to see the sun. You know, once in a while you'll be able to see it, even if there's bad weather. So that takes care of the latitude part. But the problem of having a good timekeeping device that works on a ship is that since the time of Galileo, they basically, the only kind of clocks they had for a while were the pendulum clocks. And those pendulum clocks don't work well on a ship that's rocking back and forth. They would throw them all off. And so there was a big search then for a clock, and England had a big prize for the first person to find a working clock on a ship. And you can see this clock if you go to Greenwich Village. There's an observatory there. And by the way, I guess they get the prize for being zero longitude because of the fact that they were able to solve the longitude problem with the clock. And so sometimes they say Greenwich is the center of space and time because it's 0 degrees longitude on our scale here. And so a lot of times standard time is measured with respect to Greenwich time rather than some other time, which is all relative all the way around the Earth. That you have some standard time, and so that's given to Greenwich. But this guy came up with this really cool clock that worked with springs that moved back and forth, and it was just amazing. They took it on a trip to India and back, and it only lost like 5 seconds. And they said, you know, there's no way. No clock can be that good. You know, try it again. And so they kept this guy strung out in court until he died of old age. Then they just stole his invention. But the prize in today's money would have been like $50 million or something. And so they ripped him off. But that's typical of what the government will do to you if you let them. So they got the clock. So now, to get longitude, what you need to do is to measure your time with respect to some standard event. Okay? And so if you take, let's say, a standard event like sunrise. Of course, sunrise will change from time to time, but at a particular time of the year, sunrise is happening somewhat consistently within a few minutes of being the same time. And then, let's say that this is in Greenwich. Then you go to across the Atlantic. You wake up and the sun is rising at 3 a.m. What does that tell you? That the sun decided to get up early? No. This is 3 a.m. Greenwich Standard Time, not 3 a.m. where you are. So if we look back up at the data projector, what that tells us is that if this is the time zone for Greenwich, then we must be 1, 2, 3 time zones over from that. Okay, and so if we're 3 time zones over, that's 3/24ths of 360 degrees. Okay, and so that's how we can measure our longitude. We take a ratio of the number of time zones. This is 3 time zones over. That's just like for us here in California versus New York. So if we're 3 time zones over, that's 3/24ths of 360 degrees longitude. So that's how far we are away from 0 degrees longitude. Okay. And so that's the way then that we work that out in terms of time zones and in terms of the basically measuring how much time has shifted from our standard event to where we're at in order to get the number of time zones. So then that allows us to be able to have our position both in longitude and in latitude both to pinpoint our exact location on the surface of the Earth. Of course, today, instead of doing it that way, we do it with our GPS system. And the GPS system can locate things way, way better than that. But and these days, it was done basically astronomically and with timing. Okay. Now, there are other motions that are interesting to look at. And some of these have to do with the motion of objects along the plane of the ecliptic. Okay, and so what is the ecliptic plane and how does that relate to signs of the zodiac? Well, basically, if we look in the direction of the ecliptic plane, it turns out that there are some constellations that mark out the different directions that we can look along the ecliptic plane. And so these directions then are mapped out traditionally by 12 what are called zodiac constellations. Cancer, Leo, Virgo. But here we're looking all along Scorpio, Sagittarius, Pisces, Aries, etc. We're looking basically at a coordinate system that is mapping out different positions along the ecliptic plane. So if we were to look at the same picture from a top view, this would be the sun. This would be the Earth going around the sun like this. The plane of the board would be the ecliptic plane. So if we look out in this direction, we'd see some zodiac constellations. So here'd be one, here'd be another, here'd be another. And so these zodiac constellations then tend to be about 30 degrees apart. And so each zodiac constellation then marks out a approximately 30-degree increment, or 1/12 of the 360 degrees of the ecliptic plane. And so if you're looking this way, there are also going to be ecliptic or zodiac constellations out there too. But you're not going to be able to see them until you get around to this side. And similarly, the ones that we can see now, here, we're not going to be able to see when we get around to that side. We'll be able to see these just fine. That'll be 30 degrees. This will be 30 degrees. But unless it's a total eclipse of the sun, that's the only time when you can see stars during the daytime, is during a total eclipse of the sun. And so unless there's a total eclipse of the sun, when we're in this position, we won't be able to see these zodiac constellations. And when we're in this position, we won't be able to see these zodiac constellations because the sun is getting in the way. So let's go back up to our data projector view. We can see then that the position of the zodiac constellations then varies with the time of year. Here's the Earth going around the sun. So on the back side of the Earth, then we should be able to see, say, Cancer and Gemini and Taurus. When we're over here in the June, July, August, September part, we should be able to see Capricorn, Aquarius, Sagittarius. But we wouldn't be able to see these zodiac constellations because they could only be visible during the daytime, and so it would be impossible to see them without a total eclipse. So if we go back to our star wheel for a second on the other data projector, let's just set up, again, 9 o'clock in the evening. Okay, so I've turned this around a lot. So let me just go back to 9 o'clock p.m. Remember to do p.m. when you're doing this, not a.m. That's an easy mistake to make. And then we'll set this up again. It seems like longer now, but no, this is still September the 3rd. And so now, if we look, and we see this dotted line here, here we go. We see this dotted line. That dotted line, if we look along it, now it's not this one, not the solid line, that says celestial equator. Don't worry about that. But for this one, you'll see ecliptic along that dotted line. And then that contains Capricorn there. This would be Aquarius. This would be Pisces. So that's but Pisces is near the eastern horizon at 9 o'clock in the evening. So it's not that visible. We have Aquarius, Capricorn, Sagittarius along this ecliptic line. Then Scorpius would be near the western horizon, and then maybe just a little bit of Libra. So if we go back to the other data projector, we can see then, okay, well, here's Pisces. Remember that we were saying that's kind of off near the edge, because here we are, this is like September in here. So Pisces is off that way. So there's Aquarius, Capricorn, Sagittarius, Scorpio, and then Libra is kind of off near the edge. So that kind of fits with what we were saying should be visible this time of the year. Okay. And so another thing that is interesting about this is the connection between these zodiac constellations and astrology. Okay, so a lot of you have probably been telling your friends, I've got this really cool astrology class that I'm taking right now. And then, oh no, astronomy, not astrology. But there is some historical connections between astrology and astronomy. So the idea then with astrology is that at the moment that you're born, the sun is going to be in a certain zodiac constellation. And so here we can see that this is kind of, I guess, October or something like that, September. Then we'd be, the sun would be in the constellation of Virgo. You go, well, how could you even know that if you can't see those zodiac constellations when the sun is out? And the answer is they weren't dumb. In those days, they knew where all the zodiac constellations were. And so they knew that if you could visually see some zodiac constellations, the other ones would be on the other side. And would be in a direct line with where the sun would be. And so the idea then was that at the location that the sun is within the zodiac constellations, that determines your zodiac sign. Okay, so you're a Libra or Virgo, or, and then they attributed a lot of psychological characteristics to people that were born with different astrological signs. And so that's all pretty interesting, but what they failed to take into account is the fact that your astrological sign as defined by astrology is where the Earth's axis was, in terms of where the Earth's axis was pointing 2,000 years ago. But the Earth's axis has been precessing and has essentially gone through about one zodiac constellation in its precession in the last 2,000 years. And the astrologers, for some completely unknown reason, other than perhaps to give scientists a lot of ammo to fire at them, they've not updated their charts in 2,000 years. And so you think that you know what your astrological sign is? Well, think again. This is what your real astrological sign is based on the position of the Earth's rotational axis today. And so my birthday is on March 11, and so I thought I was a Pisces. Nope, I'm an Aquarius now. And so you can go and you can check out what your real sign is based on the actual configuration of the Earth with respect to the zodiac constellations today, not 2,000 years ago. And so for some very unexplainable reason, they just left it that way. They didn't update their charts to take into account the motion of the Earth's rotational axis with respect to the plane of the ecliptic.